Hi again. So let's go over the conditions and formulas for a hypothesis test and confidence interval for comparing two means. And this is two independent means. So I can make a note there. Two independent means, not matched pairs. Okay, so just like we've been using the t-distribution for means, for a theoretical hypothesis test and confidence interval, we get our p-value and t-star from the t-distribution. So the conditions need to be met. So what are those conditions? I think they're going to look familiar to you. Independence. The individuals in each group and between groups must be independent of each other regarding the variable measured. Okay, so I'm going to underline each group and between groups. And randomization, the data are from two independent random samples or two randomly assigned treatments, right? So there's a couple different ways. If it's an experiment, they should be randomly assigned the treatment. If it's a survey or two other kind of groups, observational groups, then we would do two random samples. Then large population, always if sampling without replacement. We must be sampling from a large population to consider the individuals independent of each other. Population must be 10 times each group's sample size. So it's not the total, it's each group. And sometimes you have different populations for each group, so we'll write out our conditions a little bit differently depending on if it's both coming from a single group or coming from two different groups. Like let's say you were comparing men versus women, for example, or other multiple genders. Okay, so sample size condition. We have two sample sizes, right? So N1 and N2 greater than or equal to 30. That's one way to meet the condition. Or the population is normally distributed, or samples are nearly normal. So there's our nearly normal again. So same idea, it's just that we're expanding this to two groups. Okay, great. So let's look at the degrees of freedom. Now, degrees of freedom is interesting when you have two groups. So combining, because you don't always have the same sample size, like here we in the cartoon experiment that we're using for an example in this lesson, they had the same group size of 20 each, but that's not always the case. So there's a combined degrees of freedom calculation, and it is a complicated formula. I have it on here just to show you what it is, but I'm not going to expect you to use it. Okay, technology will do that for us. So there's two different ways to do the degrees of freedom on this. One is using technology, okay, and that'll be called the calculated degrees of freedom, okay? The other way is there's an estimated or conservative method, okay? And this was used more often when technology was a little bit more complicated, more challenging, less available. So the smaller of N1 minus 1 or N2 minus 1. So the smaller of the n's and then minus 1. Calculated one is this. Isn't that a fun formula? So yeah, it has to do with the variances, has to do with combining, yeah. So I don't expect you to do this. I'm just gonna box it up, but I thought you would be curious if I told you there was a formula, you'd want to see it. We're gonna use technology. Okay, and I'll show you where that's given in the technology. So keep an eye out because questions will say either use the calculated degrees of freedom, and they'll generally give you what that is, or they'll say use the estimated or conservative method. Okay, so there's two methods. And we will compare, we'll be comparing these two methods just to see what they look like. Okay, so let's get into the formulas. So for a hypothesis test, we need a test statistic. which is a t statistic since we're using the t distribution. And I've got a subscript of the degrees of freedom here. And then we take our observed value minus the null, right, which will be 0 in this case since it's a difference. And then we have our standard error. So this is also another new thing. It's combining the standard errors. Okay, it's a formula for that, similar to what we saw for two proportions. Okay, and we can add variances when the variables are independent. So that's why we need that independence condition in order to do this. Okay, and here's our confidence interval formula. It looks similar. Same idea. We have our difference, right? This, we call it the point estimate, plus or minus t star for the degrees of freedom. And then we have our standard error here. So you can see the standard error formulas are the same in these two. Okay. Now, you might be remembering back when we did proportions. We remember how we did a pooled, assuming the null was true, we had to pool all of our observations into one group and get that pooled proportion, right? We're not going to do that for means, so let me explain why. So this is about pooled versus unpooled tests. So we did pool the proportions for the null to get p hat c. Remember that for the two proportion test. So there is a pooled t-test, but here's the drawback with that. The pooled t-test assumes the variances of each population are the same. Okay, so that would be assuming the S1 and S2 were the same. And I don't think that that's a very reasonable assumption. It's a very limiting assumption. So here we're using the unpooled t-test. Okay. So just so you're aware that there is a pooled t-test, and you might run into that if you do more statistics, but it's a little bit tricky. So I don't want to assume that the variances are the same. And we can't assume that under the null, right? So the null is that the means are the same. There's no difference, right? But that doesn't tell us anything. So assuming the means are the same in the null hypothesis doesn't tell us anything about the variances or the standard errors. Okay, so that's why we're doing the unpooled t-test. Okay. Okay, great. Well, because the next part, we're going to go through all these formulas for the cartoon test is going to be a bit longer. I'm going to stop this video here, and then I'm going to switch over to that, and we'll go through these calculations and use the formulas in the next video. Okay, see you over there.